Okay, hi, welcome back. Okay, so I promised you that I would talk about combined heat transfer conditions, combined forced and free convection. So to remind, this is a recap of what we discussed earlier. So in the beginning of the class, well, in this chapter, we looked at the boundary layer equations and we considered the condition when there is both of those effects. In those cases, in the boundary layer equations, ratio of crossover divided by the Reynolds number would show up. And under those cases, if this ratio is much smaller than 1, we would say that free convection is insignificant. And if this ratio is much greater than 1, then the forced convection is insignificant. And we have been covering conditions where Grasov number is much larger than Reynolds number, right? And at least, we were assuming that. And what happens if we have somewhat comparable effects of those two modes of heat transfer? Then we are going to have a Nusselt number in the expression of Reynolds number, Grasov number, and Prandtl number. And this expression, among other things, is going to depend on the configuration. Like we had this discussion about flow past a cylinder, for instance, right? So how is the wind direction is affecting, natural convection and so on? It depends on relative directions of the forced and free convection, meaning depends on whether forced and free convection are assisting or opposing each other. Okay, so what I mean by that is, for instance, what you can have is, let's imagine you have a vertical plate, and that's gravitational acceleration. The surface temperature is greater than T infinity. Therefore, as natural convection, you are going to obtain a net flow in that direction with our velocity scale was u0, so I will indicate free convection by this velocity scale u0. On top of that, if you introduce an forced convection with a free stream velocity of infinity, what you are talking about is, in essence, an assisting configuration. Free convection, forced convection is assisting free convection, or vice versa. So what else? Let's talk about this cylinder case. We have a cylinder again. The surface temperature is greater than T infinity, and then we are going to have this plume forming towards up, right? U0. And on the other side, what if we have a flow that is coming from the other side, U infinity? In that case, we are actually talking about opposing flow configurations. But that's not all. How about, for instance, we have those two conditions. Let's say that's a cylinder or a parallel plate with, I'm going to, simply write, how about that's U0 over a horizontal plate, or that's U0 from an, let me write this or here. So for these geometries, if you have a flow that's coming in perpendicular, you have a transverse configuration. And now, depending on the flow configuration, we need to take this into account in different ways. That's clearly going to be assisting, opposing, or is assisting in a transverse sense. That's maybe one way to put it. And this is a complex subject, and it requires its own studies, its own research. And however, to a first approximation, we can come up with a first approximation. I would like to emphasize this part is first. That's very important because the subject itself deserves its own attention. You need to develop the expressions for Nusselt number for specific configurations based on this functional relationship. However, in the absence of specific correlations, we still do a first approximation. It looks like that. So the combined Nusselt number is going to be a function of Nusselt number for the forced convection conditions isolated alone, right? So we are dividing the problem in half, and then Nusselt number for the free convection. Sometimes we can also call this natural convection, and this is more convenient to define a subscript like n, that's subscript like f when you are writing down. And this can be, these are raised to a certain power n, and depending on the flow arrangement, they can be plus or minus. And all of this is raised to the power of 1 over n, an exponent n. So first of all, let's talk about this flow arrangement. If you have an assisting or transverse flow, you are using the plus sign because it's enhancing the heat transfer. But if it is opposing, then that actually has the effects of reducing the rate of heat transfer. Therefore, one thing. So in general, what is this exponent? N is equal to 3 is good in general. But studies indicate that if it's a transverse flow, N is equal to 7 over 2, or N is equal to 4, again, without citation of any further information like the specifics of the geometry, that's the best we can do. But this is, you can pick one of those if it's the transverse flow. Yeah, pick one. That's all we can say at that point. And yeah, you can come up with the first approximation for the combined heat transfer conditions, free and forced convection, based on this expression. Let me clearly indicate that these are two separate items. And finally, maybe I should point out that, well, for laminar forced convection, effect of free convection, either opposing or assisting, is going to be, can be significant. However, usually it is negligible when the flow transitions into turbulence, the forced convection flow transitions into turbulence. Okay, so a very quick illustration of how to apply this concept. I remember people were asking about this in this section or the other section. In problem, we were solving problem 9.56, revisited. When we were solving the problem in part B, we were talking about a breezy day with wind speed of 8 meters per second. Now the question is, we individually calculated force and free convection problems. In part A, we found that Nusselt number is equal to, let me actually write it this way, Nusselt number for free convection is equal to 21.03 based on an Grashof number of 5.3 times 10 to the power 6. In part B, we obtained the forced convection conditions. Okay, so forced convection conditions of 97.63, and we calculated it based on our correlation from chapter 7 using Reynolds number of 2.90 times 10 to the power 4. Okay, so we are being asked to calculate the combined effect, like the Nusselt number, and we need to make an assumption. This problem doesn't give us enough information how to treat this problem. I'm going to assume that this is a hot surface, so therefore is there is going to be this plume forming in the vertical direction, right? And what if the breeze is actually coming from the bottom and going up? So let's assume that's the case. Let's assume a system flow. First of all, we need to check and see whether we need to actually apply combined conditions. Or the question is how much error we were making by not considering the combined conditions. So when you look at this ratio, that turns out to be approximately 0.006. It is much smaller than 1, meaning that in the presence of forced convection, the influence of free convection is going to be somewhat small, but we still would like to go through the action and make a calculation. So let's do this. Combined effect. Assuming a system flow. Under those cases, we are going to calculate the Nusselt number, the average Nusselt number under combined conditions is equal to 97.63 raised to the power 3 plus the 1.03 raised to the power 3, all of this raised to the power 1/3. And when you do the calculation, you are going to see that that's very close to the forced convection conditions. And in effect, what we're getting is approximately 0.3% increase. And that's actually much less than the uncertainty associated with the correlations that we are using. So I wouldn't call this very significant. In heat transfer due to free convection. Does this make sense? So this is essentially how we treat a combined forced and free convection problem. Okay. So what I would like to do is solve an example problem about this chapter. Here is problem 9.83. We have a neutral convection air heater that consists of an array of parallel, equally spaced vertical plates. They are maintained at a constant fixed temperature of Ts, and there are embedded electrical heaters that's causing that. We know the dimensions of the plates. It is indicated in the figure as well. And they are sitting in a quiescent atmospheric air with ambient temperature of 20 degrees Celsius. So this is an optimization problem because we have a limited footprint area, limited space. We are being asked to contain this array within a distance range of 150 millimeters. So the surface temperature is given. And the question is, what is the plate spacing that maximizes the heat transfer from the array? And for this spacing, how many plates comprise the array, and what is the corresponding rate of heat transfer rate from the array? Let me bring an inset of this problem to the corner of my screen. And if you are wondering how a natural convection air heater is looking like, here is one. This is how it looks like. And let me actually use this figure to annotate what we are being asked. Okay, so we are actually looking on one side of this heater, and I'm going to go ahead and annotate. Let's say that's the gravitational acceleration, and that's the distance. For the plates nomenclature, remember, we would have this distance L. That's not the spacing, that's height of the plate. And we are assuming x direction, increasing in that direction. What is L? L is equal to 0.3 meters. And then we are discussing about what is given in the question is this width. And the width is equal to also 0.3 meters. The surface temperature of this array is 75 degrees, and the ambient temperature is 20 degrees. And the question is, we would like to fit all these fins into the footprint of well, the figure is not to the scale for our parameters. The width of the array is maximum should be 0.150 meters. So, well, it needs to be more tightly squeezed according to the figure. All right, so we are going to be, what is the first question is, what is the spacing X that maximizes the heat transfer from the thin array? Is this S max or S optimal? Well, A or B? So that's the question, right? I will ask you that question. I forgot to publish the last poll. I already published it. So let's hear from you guys. What do you think? What are we being asked? Is this the maximum S parameter we discussed, or is this the optimal spacing parameter S optimal that we discussed? I will call it a day when we have more than 12 people. One more people, please. One more person. Okay. In the last moment, there was an A answer. But you don't see clearly from the webcam, but my eyes are watering because of this beautiful scene of vast majority of the class coming up with a correct answer for this. That's right. This is optimal, right? So because we are maximizing the heat transfer, not the convection heat transfer coefficient. It is important. It's not only something conceptually important, it's also important for the analysis because we are going to be using the calculations for the optimal. What is the optimal spacing? So when you look at this table over here, first of all, which part we are going to focus on? Now, I'm not showing you the right one. Hold on a second. There you go. So we have 4 conditions. We are looking at symmetric isothermal plates. We are going to be using this parameter, and for S optimal, we are going to be using this. Let me write down right over here. So S optimal is going to be 2.71 times Rayleigh number divided by S cube multiplied by L raised to the power of -1/4. Okay, so that's the equation we are going to use. How about the parameters we are going to use for equation 9.45? These are the parameters are highlighted in the table. That's 576, and that's 2.87. That's right. Let me check. It has been a while since I took a look at that table. Yeah, okay, so 576, 2.7. Let me in full write what this is about. That's a symmetric isothermal plates. Okay. So the reasoning is we are using table 9.3. I think I skipped to mention that. Let's evaluate the fluid properties for isothermal plates. We are using the film temperature. That's 320 kelvins. Once you do the evaluation, you are going to obtain kinematic viscosity as 17.90 times 10 to the power -6 meters squared per second. Thermal activity as 27.8 times 10 to the power minus 3 watt per meter Kelvin, Prandtl number of 0.704. We can calculate the Rayleigh number based on the spacing, right? Let's try and do that. Rayleigh number is G beta Ts minus T infinity s raised to the power 3 divided by mu square multiplied by Prandtl number. Let's substitute the numbers in. 9.81 times 1 over 320 times 75 minus 20. Uh-oh, we don't have the s value, so they are going to simply write s cubed over here and continue. 17.90 times 10 to the power minus 6 squared multiplied by 0.704. Under these cases, we are going to obtain Rayleigh number as a function of this spacing, 3.705 times 10 to the power 9 multiplied by s raised to the power 3. Okay, so we couldn't do it numerically or function of as a nonlinear function of spacing, but S optimal is going to help us to determine this spacing. That's going to be 2.71 times Rayleigh number S divided by S cubed L. So this S cubed is going to get cancelled out. So we will be able to obtain a numerical value for that spacing, 3.705 times 10 to the power 9 S cubed divided by S cubed multiplied by the length 0.300 and raised to the power 1/4. And this optimal spacing is going to be 0.00813 meters, and that's going to be 8.13 millimeters. So these plates that are 30 centimeters in height and width are going to be close to each other in approximately less than a centimeter distance, something like this. They are going to be very close to each other. That it turns out that that's the spacing that maximizes the heat transfer. So let's let this spacing to be this specific number. And then we can calculate the Rayleigh number as 1991. And the Rayleigh number multiplied by S over L is going to be 53.5. The reason I'm doing this is that the calculations are involving actually this parameter rather than the Rayleigh number itself. So let's substitute down divided by 53.95 square plus 2.87 divided by 53.95 raised to the power 1/2. All of this raised to the power minus 1/2. Okay. At the end, we obtain the Nusselt number as 1.303. And let's calculate H from here. 1.303 times 27.8 times 10 to the power minus 3 divided by 0.00813. And average convection heat transfer coefficient is 4.46 watt per meter square Kelvin. Okay, so we are being asked to calculate the number of plates. So that's a simple geometric calculation. With the given spacing, how many plates we can fit in, that means and number of plates minus 1 multiplied by the spacing should be less than this threshold constraint that we are given as the maximum array width. And from here, from this inequality, you can develop an expression for the number of plates. And that's equal to 0.150 divided by 0.008 13 plus 1, that's going to be 19.45. So we are being able to fit at least, at most 19 plates, right? So we need then round it. We need to round this down. So we are going to have 19 plates within this. That's the answer, the first part of the question. And the second part is, I also need to make sure that, so this is the first answer of what was being asked. And the last thing that was being asked was the heat transfer rate. It's quite easy with this information. The surface area multiplied by Ts minus T infinity, where the area is going to be one plate area, and they have two faces each plate, right? So we are going to multiply this by 2 times the number of plates times the footprint of a single plate, WL. That's going to be 2 times 19 times 0.300 times 0.300. And as a result, we obtain a total surface area of 3.42 square meters. And that's going to give us 4.44 times 3.42, 75 minus 20. And we obtain the heat transfer rate as 835 watts. So again, let's put this into the perspective. We have a system. Let's go back to this system. And the system has these dimensions, these square plates of 30 by 30, something like this, right? And we are assembling 19 of them side by side with a spacing less than a centimeter. So all of them are stacking together and looking like this. So this is the structure. And it is able to dissipate for a temperature difference from 75 to 20, about 55 degrees. It's able to dissipate about 835 watts with natural convection. Imagine if you needed to cool down your GPU or CPU on your computer by attaching one of those. It will be quite bulky. And that's why in the computers we have forced convection cooling to be able to do this in a more limited space with less heat transfer surface area, right? Because we'd like to increase H. So free convection, on the other hand, is quite maintenance free because you don't need to maintain a fan. You can attach this to power systems that are on the outside. They're not affected easily by the outside weather conditions, and still they are able to dissipate a decent amount of heat. You can see that 835 watts is quite decent. Okay, so any questions about the example problem? Okay, so that's the end of our chapter. And chapter 9. And I would like to emphasize that we didn't cover sections 9.8.2, 9.8.3. These are not included. We are not covering them. These are about the concentric cylinders and spheres I mentioned earlier. They are using the formulation for effective thermal conductivity. It's simple. You can go ahead and take a look at them. They are not complicated. And there is also one chapter that we didn't cover at the moment. That's 10.9, that's mass transfer. And I'm going to ask you to revisit this as a reading assignment at the end of the semester. After we cover the topic. We are not going to individually treat each one of those cases for mass transfer because heat and mass transfer analogy already gives us a general way to actually understand the forms of the correlations. I'm going to ask you to go and read them, and if necessary, you can apply them. Finally, problem 19. Problem 9.92. I recorded a video lecture. I'm going to make it available after the class. I have another class now, but I'm going to enable it after that class. So let me show you the example problem. So this is the problem. And this is about the enclosure, the keys. And a quick run through is that we are interested in two different sections with identical dimensions, but however their orientations are different. The bottom surface is heated because it is looking at the interior versus the top surface that is looking out on the outside. And the vertical section is heated on from one side again. However, what we are doing is, first of all, we are trying to understand what is the effect of this orientation, horizontal versus vertical, because their dimensions are identical. We are going to be able to evaluate the amount of heat loss from those individual panels simply based on their, orientation. So horizontal versus vertical, which one is going to cause greater heat loss from the dwelling, the urban dwelling? And secondly, potentially to introduce some additional structural integrity, we are adding some elements like baffles right over here. So that's actually creating additional, separate spaces, like two different cavities, that has the effect of changing the H over L ratio that we have covered in a vertical cavity. Remember that it's quite important what kind of H over L ratio that you have. So this baffle is actually has the effect for our calculations of changing this H over L ratio. And we are being asked, is there going to be a heat transfer consequence or heat transfer effect when we introduce this structural element into our wall section? All right, so for the rest, you can go ahead and take a look at the video lecture. And if you have any questions, you can always ask me. I have office hours today on what was the time? It's at 3, between 3 and 4, I believe. That's what I posted. You can check the announcement. And this is going to be an online office hour where I'm going to be here in the class. And I will be answering the questions that are coming from you guys. Okay, so having said that, we have a little bit more time. So how about giving a start to our new topic? Chapter 10, we are talking about boiling and condensation. We are going to be starting with discussing boiling and then move on to condensation. And boiling is typically, as we know, this due to evaporation of the fluid at the surface liquid interface. So we are now considering the problem as a combustion problem where the phase change is involved, either in terms of change from liquid to gas or from gas to liquid. Okay, so what happens here is, imagine we have a surface with a surface temperature of Ts that's greater than the fluid temperature, that's the fluid that's in the liquid form. What's going to happen is that due to the phase change in the liquid, we are going to have bubbles forming, right? So there's going to be like these bubbles forming from the surface, and then they are going to move up. Why is that the case? There's going to be the density of this vapor of the same substance is going to be much lesser than the density of the liquid. And that's going to give us a buoyancy force That's on the order of G, density of the liquid minus density of the vapor, right? So that's the buoyancy. So that's a significant buoyancy force within the fluid. That's actually also going to cause this. They're going to be space generated, and that space is suddenly moving up, and therefore the space is going to be replenished by additional liquid. But there is this, due to motion of the bubbles, there is going to be this advection of the liquid that is rushing in, and let me actually write this down. The fluid motion is going to be induced by two mechanisms. By one, the density differences. That's similar to free convection. And two, the movement of liquid due to formation and motion of the bubbles. So let's call this displacement of liquid due to formation and motion of the bubbles. Okay. All right. So, so there are two mechanisms for heat transfer. First of all, you are going to notice that we are going to have this, we know how to treat the solid, right? So that's the surface, and there's going to be the surface temperature anti-infinity. If you plot this temperature like this, there's going to be, going to look something like this, right? And there's going to be some slopes associated right over here. And this is going to be due to, the typical treatment that we did, like the free and forced convection happening and the heat transfer due to the temperature gradients. And liquid is going to come in and displace, move around the surface. That's going to be kind of combination of free and forced convection. And the heat transfer due to temperature gradients within the fluid. Okay, why am I writing this tiny at the corner? Because that's not the main player in the field. The main player is actually what's happening inside the bubble. So imagine this bubble is actually an energy carrier now. What is the energy that's being carried? Energy that is trapped within the bubble compared to the surrounding is the density of the vapor multiplied by volume of the vapor multiplied by the enthalpy of the vapor. That's my enthalpy now. Let's not confuse it with convection heat transfer coefficient minus density of the liquid, volume of the liquid multiplied by enthalpy of the liquid, right? But in essence, when you write it this way, you might be asking, why are you not writing this as some mass multiplied by this latent heat of vaporization, right? HFG. So now this is essentially the main player. There is very high energy density due to latent heat associated with the phase change. All right. So this is a complex process, this formation of the bubbles and traveling of the bubbles. We know how they travel, it's the buoyancy force, but the formation of the bubbles are also going to be influenced by what's called the surface tension effects. The surface tension effects are are essentially the tendency of the liquid interface to minimize its energy. And liquid, in essence, it's liquid interface acting like an elastic balloon, and there's going to cause some pressure differences within inside the bubble and the surroundings. And it's going to affect when is that going to bubble sustain itself, when it's going to burst. So surface tension will turn out to be an important property of the liquid that we are going to take into account. So to sum up, boiling is a complex process. We are considering both the traditional wave free and forced convection because of this fluid motion, buoyancy force is there, the predominant liquid displacement due to motion of the bubbles there, but the bulk of the energy is not carried by this sensible effect. That's sensible heat, right? So let me write this. This is essentially, this part is we are sensible heat due to temperature gradients, but the bulk of the energy is carried by the latent heat. And this additional mechanism of heat transfer allows us to be able to transfer a large amount of heat across a small temperature gradient. So we are actually cheating the game. We are breaking the limits of what you can achieve over a certain temperature gradient. Large heat transfer rates. Even across small temperature gradients. Right. So let me actually illustrate what kind of convection coefficients we would expect. That's in the very beginning of your textbook, table 1.1. And you can see with the phase change, we are looking for a whooping of somewhere between thousands to up to 100,000. So this is when you compare this to forced and free convection, you can see how much more effective you can. And that's the reason why we are actually encountering this phase change phenomena as a way to transfer energy from one location to other. Most typical ones are power plants, refrigeration, electronic cooling. And that's the point where I would like to solidify your notion of those cycles, right? So when we have thermodynamic cycles, either a heat engine or a refrigeration or heat pump cycle, we actually have multiple heat transfer components. We actually have two heat exchangers right over here. One is a boiler and the other one is condenser. And it's not a coincidence that these are heat exchangers that are dealing with convection heat transfer by phase change, because that's one of the most efficient ways to realize heat transfer and over small temperature gradients. And in order to, you might be wondering how a boiler looks like. So here is a boiler. That's a schematic, and that's actually a boiler that's almost the size of a building. And that's the one you can typically find in a power plant. That's a boiler, but your heat exchangers doesn't have to be that large to deal with phase change. So here is another one. So these ones that over here, that is transferring heat from let's say a CPU to an heat sink. This is actually like highways of heat transfer, where we are actually, that's what's called a heat pipe. These are transferring heat, conducting heat using phase change rather than the conduction process. And you may not know this, but heat pipes are all over the place. They are inside your phone. They are inside, compact mobile computing devices like laptops. And these are essentially things that you might take into consideration. I would like to show you a video, and I will post the link of the video to the chat window if you like to leave and watch it on your own time, or otherwise you can sit here together with me and watch the video. So here is, let me start this and actually get the video link. I'm going to post it over here, but if you like to stay with me, that's a 2-minute video. Let me show you this on the screen.
Heat pipes are fully sealed, passive two-phase heat transfer devices that take advantage of a fluid's high latent heat of vaporization to achieve extremely efficient heat transfer. A heat pipe is comprised of an envelope, a wick structure, and a small amount of working fluid. The fluid is processed under vacuum, which allows for two-phase operation across a wide temperature range. During operation, heat is input in what is known as the evaporator. The heat boils the fluid and pushes the fluid vapor to the colder region of the heat pipe. The colder region, which is typically coupled to a heatsink, is known as the condenser. The fluid gives up its latent heat and condenses back to a liquid and is again absorbed in the wick structure. The wick structure then passively pumps the fluid back to the evaporator. This entire operation results in an extremely low temperature difference across the length of the heat pipe.
So,
the efficient rate of heat transfer compared to a solid copper rod.
as you can see
Both
over
the heat
here,
pipe
we are
and the copper rod
essentially
are coated with thermochromatic paint, which will change color as it transfers heat. We'll start by moving the copper rod to the hot zone. Copper is known as a very strong thermal conductor. It has a thermal conductivity of roughly 400 watts per meter K. As it transfers heat, you can see the color change from the base of the copper rod upward. Now we'll move the heat pipe into the hot zone. As you can see, as the fluid vapors and transfers, the heat pipe rapidly isothermalizes and has a very consistent temperature across the length of the heat pipe. Now we'll move the copper rod and the heat pipe back to the cold zone to show that the heat pipe can work in adverse orientation and still is able to provide the same high effective thermal conductivity.
Once you have heat transfer, convection heat transfer by phase change at your disposal, you can achieve really high amounts of heat transfer rates. Okay, anyway, that's it for today. In the next class, we are going to continue with the